For centuries, electricity and magnetism were seen as two separate forces. That changed in 1820, when we realized that moving charges actually produce a magnetic field in the space around them. Hans Christian Ørsted proved this during a lecture when he noticed that current in a straight wire caused a compass needle to deflect on real-world complexity, knotted bundles and intricate coils, where the geometry is far from linear. In these systems, you can't use a single top-line equation to find the magnetic field. The angles and distances are constantly shifting, making it impossible to predict the field at any one point without a more precise tool. To solve for the field of a massive, complex wire, we have to look past the whole and focus on the individual microscopic parts. This is the core logic of integration. We break a sprawling, curved shape into an infinite number of tiny, straight segments that we can actually measure. We define this tiny slice as a current element, represented by the vector IdL. It serves as the fundamental building block of magnetism. If we isolate just this one pulsing segment, how much does it contribute to the magnetic field at a specific point in the empty space surrounding it? In the 1820s, French physicists developed the mathematical framework for this calculation. It is called the Biot-Savart law, and it defines the field produced by these tiny segments so they can be summed into a final result. This spatial relationship maps a curved conductor, a tiny current element IdL, and a target point P. A displacement vector, r, connects them, establishing the physical distance. This creates a specific angle, theta, between the current flow and the target path. The resulting magnetic field segment is labeled dB. Its direction is always perpendicular to the plane containing both the current element and the displacement vector. The Biot-Savart law formalizes these vector relationships. The strength of the field at point P is determined by the specific spatial orientation of these variables. Field strength is proportional to current and segment length, but diminishes rapidly with distance squared. In a vacuum, we include mu0, the permeability of free space. Finally, multiplying by sine theta accounts for the wire's angle relative to point P. This formula allows us to predict the magnetic field for any individual segment, no matter how the wire as a whole is shaped. This is easier to understand if we compare it to Coulomb's law. In electrostatics, a stationary charge produces a radial electric field that pushes or pulls in straight lines. But magnetism is different. It doesn't move in straight lines from the source, it curls. The magnetic field is always perpendicular to the charge that produces it. Despite these differences, both laws follow the principle of superposition. This allows us to calculate the fields of several different sources and simply add them together as vectors. While both share an inverse square foundation, magnetism adds a layer of geometric complexity. The field's direction isn't just about where the charge is, but the direction it's moving. You can find this direction using the right-hand rule. Grasp a wire with your right hand. Point your thumb toward the current, and your fingers will curl in the direction of the magnetic field. Because of the sine theta dependency, the magnetic field actually vanishes if the observation point P is located directly along the axis of the wire. This law is the foundation for virtually everything in modern electromagnetism, from the coils in a galvanometer to the powerful magnets in a particle accelerator. The Biot-Savart law is the ultimate building block. It allows us to take the movement of a single charge and translate it into a three-dimensional map of magnetism